welcome back everybody. So we are halfway through our last normal week. Next week will be closed week, and the materials I have posted so far are just one single sample final exam list. So if you look at these will be decent problems that you can start right now to practice for the final exam. Other things I would like to post very soon, possibly over the weekend, are more sample final exams, as well as a document that'll tell you the notes that will be provided on the final exam itself, so that folks can get started on producing their note cards sooner than later. Any questions about the final exam at the moment? Okay, it is going to be held on April 29th from 8 to 10 p.m. That is a pretty rough exam, but I do grade it with that in mind, that folks are doing a night class at an hour later than usual for a 2-hour exam. So just do your best, and it will be all right. Other things to keep in mind are that over the closed week, we're going to be reviewing about half of that week. So around the middle of Wednesday is when we'll complete the last section, I believe that is 10.4, and then we'll be switching to review. But other questions about where we're at or where we're going so far? Mm-hmm. Yeah, absolutely. So part of what we're going to try to do is synthesize the whole course, which is really hard to do. We're also just going to practice actually taking an exam in its own right. So I'm going to be coming to class with an actual final exam, just say a dress rehearsal version, and we'll, on Thursday, take it as if it was the real final exam. So that will provide you with extra tools to decide what are the problems that we really need to focus on, what does a real final exam look like, and things like that. Other questions about that so far? Mm. Yeah, but one sad thing, and it is really sad, is that it's going to be impossible to ask a question, even just a single question from every section, from someone all down the line. So usually what I do when I write this final exam is I look at the big questions I'd like to ask, and I pick maybe, if it's a 20-question exam, that's kind of on the high end, about 20 that looks like it's encompassing evenly the entire course. So nothing is kind of concentrated in one spot or the other. So there may or may not be a 7.1 question. Sorry for integration by parts fans. There may or may not be a question from 7.3. I think that was trigonometric substitution? Yeah. If I ask a trigonometric substitution question, however, then all the rest of the exam is probably going to be shortened because those are long questions. But once we get down to, say, the very end of the course, what am I looking at? Is this the right class? This is trigonometry. Hang on. Once we get to the very last bit of the course, here we go. So this is the right, okay, 10.4. Hang on. Is this the right class? Yes. Okay, so once we get to the last part of the class, one thing that we will not be able to do is, or one thing that we will do is ask exactly one question from each of those sections. Possibly 2 questions, but only if they're short. So when the final exam says that it's comprehensive, there's an emphasis on these sections. It's not going to be a terribly huge emphasis. So I would say those highlighted sections, when I go to calculate the point distribution on the exam, I probably wouldn't want that to be weighted more than, say, 30% of the entire final exam. So that portion highlighted will be about 25 to 30% of the final exam, where you can expect 1 question each. Then it'll just be a rough sampling of the rest of the course for the rest of it. Other questions about that? Yeah, I'd be okay with that. One thing I was thinking about doing was possibly doing maybe a page of notes front and back. But what we could do is I could do a page of notes, just one side of certain things, and then I could allow people to bring in another page of notes about like this, one-sided, and fill out whatever you'd like on it. How do folks feel about that as a procedure for the final exam? That seem about all right? Okay, I'll have to think about that a little bit more, but once we come back from class, I'll make a modification somewhere right here on what we might decide to do. If you have strong opinions about that, you're encouraged to talk about it after class, send emails, things like that. Yeah, I'd be okay with, instead of going 2 pages, 1 page or things that will be certain, and then you can bring in a page of whatever you'd like. That might be a good idea since I was going for 2 pages also. People get to decide what they need to support themselves without having me pick and choose what I think is the most important. Other questions about that? Okay, so let me make a note of that so I don't just say I'll do that and forget. I'll just say final and note card. Okay. Other questions that folks would like to discuss then about the final exam or the material we've been going over? Okay, I think that's the end of our announcements then today. So we're off to the final chapter of the course, chapter 10. We're not going to complete all of it since we are running out of time. And we may not be able to do every single topic for all the way from 10.1 to 10.4. But one thing to note when you're studying for these sections is that 10.1 and 10.3 are considered to be more of our review type sections. 10.1 is probably new to a lot of people, but 10.3 is about polar coordinates, which if you take in trigonometry, you will have been exposed to it once. But we'll teach these two sections as if you've never seen it before. The major sections are 10.2 and 10.4, where that actual calculus happens. So this is kind of a strange chapter in that sense. We'll start with section 10.1. Let's see if there's any questions first. Okay, so in 10.1, our job is to describe what in the world we mean by parametric equations. And then the whole purpose of chapter 10 is to do calculus on these new types of curves or equations. So first let's start with the definition. And it says to begin, suppose that the variables x and y are functions of a third variable we'll let the third variable be t. Sometimes it's going to be theta. If you're in section 10.3, 10.4, instead of t, you'll use the Greek version, theta itself. But we have two variables, x and y, that are a function of the third variable, t. And here, this just means that x is going to be some function of t, and y is some other function of t as well. So we'll call x f of t and y equals g at t. It'd be okay to just use f at t and g at t in place of x and y in the entirety of chapter 10, but it would just get tedious to work with. So that's the purpose of occasionally just leaving it as a variable. But now we have to be cognizant that the variable is now a shorthand for an entire function, and now there are two functions at the same time that we have to worry about. Instead of the usual y equals f of x, which is how we've been doing calculus up to this point, with a single variable representing a single function, and x just being the parameter from before. So this is our new point of view. We're adding a new function into the mix. We can now say, then, the point xy, which is also needs to be thought of as f at t, comma, g at t, traces out a curve let's call this curve C in the xy plane. So what we'd like to do on that curve C are answer questions along the lines of what is an equation of a tangent line at some point to that curve C, or maybe something along the lines of if we rotate that C about an x-axis or a y-axis, what would be the volume of the resulting surface, or maybe a question on what is the length of that curve C. And one thing to note are those are all questions we've answered before, but now we have to change our methods a little bit for every single process because this is no longer the single variable calculus we've been doing before. So all of our methods change a little bit, but once you see what the adjustment is, essentially the entirety of chapter 10 becomes one big set of review problems. Well, mainly 10.2 and 10.4 where we get to the calculus portions. So that's our definition so far, and a picture that could go along with it would look about like this. Let's just say, for convenience, everything is in quadrant 1. I'll have a point that goes from here to here. So my curve is going to have a finite length. It doesn't have to. The curve could be infinitely long if we like. And this would be my curve C. Then this point here would be f at t naught, g at t naught. The point up here would be, say, f at t1, g at t1, and this would be the terminal point. and this would be the initial point. And what we've done so far in this diagram, if we have a terminal point and an initial point, again, not all curves have terminal or initial points, think a circle or just a line itself, but if we do have those, then this implies that the domain of t, which was our parameter, is from t naught up to t1. So that's the domain of the parameter t. Notice what's interesting about this is I don't have any information at the moment until I actually evaluate f at t naught and g at t naught, what the coordinates would be from here and here, because where the location is on that point now depends on where t is. So if we take the right value of t, this would be an xy for some t, where t has to be between t naught and t sub 1. So that's the picture so far. What we ought to do very next is actually sketch our own parametric curve just to see how these things go. Any questions so far with what we've produced? Okay, maybe one last definition because it does come up quite a bit. We say x equals f of t, y equals g of t is a parameter, sorry, I have to sound this out, ization, that's a long word, of the curve C. Here we had to unfortunately use the indefinite article because there are infinitely many different parameterizations of that curve C. It's possible to parameterize this so that this initial point is really a terminal point and the curve is generated in the opposite direction. So one thing that we often have to do with these curves, if we want to capture the parameterization in the direction that it's swept out, is we can occasionally add arrows to it, going in that direction. Even if we don't have an initial point, we can still say what the direction is for that curve itself. Any questions about that so far? Okay, so common applications to something like this, a really fast application, is this could just be some particle now moving in a two-dimensional space. Notice that in calculus, we've only been considering a particle moving along a single dimension, and that was it. This can now be a particle that moves in 2 dimensions, and we can ask important questions along the lines of how far did that particle travel as the time t went from t naught to t1? So we can find the length of that curve and other interesting quantities. But first, we need to see how to work with and generate those curves and how to deal with multiple parameterizations as well. Any questions first with the definitions? Okay, so let's go to an actual problem then, using these tools. First problem we're going to do is more of a sketching type problem. It tells us to sketch the curve C that is parameterized by and let's go for our first curve, x equals 1 minus 2t, and y equals 1/2 t minus 1. And for some problems, this would possibly be the only information that's provided, but occasionally we have a specific domain for the parameter t. And that would be this last part, where we have that -2 is less than or equal to t, which is less than or equal to +4. Then the last part of the problem says, then eliminate the parameter. That's really strong language, but we're also going to eliminate the parameter altogether to find an, let's say, a rectangular or Cartesian equation of this curve. That is a really long set of instructions, but it's finally on the board. And this is something you could be asked to do on, say, the final exam. I think that'd be an OK 10.1 type of question. So there's 2 things to do here. First, we actually have to sketch the curve that is given by this information. So that's where we'd start. And sketching this as a curve is different, but it's not too different. If I want to sketch this curve, I just need a series of points, and I'll just connect the dots. So to generate those sequence of points, we do need an x-coordinate, a y-coordinate, but the value of x and y depends on what t is as well, since x and y are both a function of t. So we think of this as being f of t, and this as being g of t at the same time. Now we pick the values of the parameter and go from there to sketch the curve. So first thing I want to do is, if there is a finite domain, I'd probably pick the lower bound of -2 to start it off. After doing this in class or for homework, then you don't have to go too carried away. So probably the next value I'd go for is maybe not all the way to 4, that's a bit much. There could be some curvature on the curve C that we may miss if we go too extreme. So maybe I'll go up to 0. Step size of 2, then do 2, and then 4. So something like that ought to do the job. If you're getting, say, 10 points, you're probably working too hard, which is not bad if you enjoy it. But I would say around 3 to 4 points should be sufficient for the homework problems and for an exam. Any questions to that step? Okay, so we're trying to sketch the curve C. Every point on the curve C is of the form x and y for a particular choice of t. So we started with t to determine the coordinates x, y that we'll actually plot. So now that was a -2. We plug in -2 for x into the function f of t, or we can just think 1 minus 2t is the f at t, and that would give us a value of 5. Plugging in -2 here would give us altogether -1 minus 1, so -2. And then we just keep on substituting in all the way down. Does that make sense how the substitution works so far? Okay, so let's do at 0. That shouldn't be too bad. We would get 1 for x, -1 for y. At 2, I'll get 1 minus 4, so -3. 2 here will give me 1 minus 1 for a 0. Then finally, check the parameter t to be 4. I would get 1 minus 8, so -7. 4 here would give me 4 times a half, so 2 minus 1 for a +1. Provided I did all of that correctly. Does that look all right? Yeah, question? Get the 5 or -2? On the -2, I plugged in -2 for the parameter right here, and it became a half times -2 minus 1, just like that. And then we got a -2 altogether. Other questions about that? Okay, step size of 2 turned out to be lucky, but if I also was looking at this, I'd probably always pick things that are multiples of 2, just so that the half could cancel out in this problem. That just makes it a little bit nicer. So the next thing to do is just sketch the curve that's obtained by those 5 different ordered pairs. One thing you should definitely have on your curve is the initial point and the terminal point, provided you have a finite domain for the parameter like this. So the fact that we started at t is -2 and t equals 4 means we're on the right track for getting the entire curve itself. Then once we go to sketch the curve, I have a point at 5, 1, 2, 3, 4, 5, down -2. So that would be the first point that was obtained. And this is now the initial point. What makes it the initial point is we took the initial value of the domain for the parameter to get that point there. Then the terminal point is at -7, 1. But let's go say 1, -1 would be this point. -3, 0 is this point. At this stage, what is the actual curve that we're looking at? What would you predict we're actually plotting here? X equals 1 minus 2t, y equals a half t minus 1 is the equation for a, would you say it's maybe a parabola or? Any guesses what it could be? Let's throw in maybe the final point, which is at -7, 1. 1, 2, 3, 4, 5, 6, -7 at height 1 gives us this point, and that's all I have. But however, keep in mind this point is special. This is their terminal. point. So we have an initial point here, a terminal point here, and if I sketch this completely accurately, that looks a little bit high to me, would you folks agree that that would just be a line segment? Yeah, so the curves x equals 1 minus 2t, y equals a half t minus 1, if we put them into a parameterization for a curve in the xy plane, this is what we will get. Just an ordinary line segment. So we've done it, we've sketched the curve. But keep in mind things that you should look out for if you do this as a homework assignment or an exam problem is you cannot go beyond the terminal point if there is a terminal one. And this is what produced a terminal point. You cannot go beyond the initial point, even if it's a line, because the curve itself is just that. And there is more hidden structure on this curve. There is a direction that it was swept out. So the homework problems and exam problems will also ask to indicate the direction, but the direction with the arrowhead would always be from initial to terminal. If we didn't have an initial or terminal point, it would just be the order in which the points were being propagated. So if I went right to left like we just did, it would imply the arrow goes in that direction. So that'd be the entire sketch. So just keep in mind you have to have a directionality to the curve, and the curve has to obey the domain for the parameter itself. It can't go beyond those points. And that's the entire sketch. Any questions so far about that? Okay, so we've done half the problem where it's said to actually sketch the curve C. Now that we know this curve C to be just a line segment, it wouldn't be too bad to find an equation for that just using first principles. But the problem says eliminate the parameter to find the Cartesian equation. So that's a fancy new way to do it. Let's do it that way. And if you'd like, you could do it the original way just as a check to the process. So this is the process of eliminating the parameter t. When we try to eliminate the parameter t, this is our goal. No, I think I erased it. Our goal is to get to this point. We just want to bring it to our Cartesian equation that we know and love, y equals f of x. We know it's going to be y equals mx plus b for the right domain, but that's what we're going for when we eliminate the parameter. So if we start and we want a function y equals f of x, it means we should first solve this variable for t. So step one, solve for t in 1 minus 2t equals, I wrote that in a weird order, x. I guess that's not too inappropriate if we're solving for t. Then once we get the solution for this, we'll just substitute it back into the equation for y, and that produces the y equals f of x. So first, solving this for t just amounts to subtract 1 from both sides. Negative 2t would be x minus 1 divided by negative 2, and t would be x minus 1 divided by negative 2. So we've done it. You can multiply both sides by negative 1 if you really want to make it be t is equal to 1 minus x divided by a positive 2. Doesn't really do much for us, but the book does that constantly. So if you check the back of the book would always multiply by negative 1 over negative 1 to make the denominator look nicer. Now it's a positive 2. And if you distribute negative 1 through, it'd be negative x plus 1. So the book changes the order of that to 1 minus x just because it looks nicer. So you don't have to do that, but it's a decent thing to do since it happens quite a lot in other textbooks. So that's our step one. Step two is just to substitute the result in for y. So we go back to the second equation, y equals g at t, and this becomes y equals a half of t, but we now know that t is 1 minus x divided by 2, and then there is a minus 1. Well, I should probably erase that. So we've done it. All we have to do now is simplify. Any questions with that step on the substitution? Okay, so now y is equal to some function of the variable x. We can say, if we say distribute, this is altogether 1 minus x divided by 4 minus 1. So now y is equal to a half, or rather a fourth. Dividing this 4 to here would give us minus a fourth x minus 1 is the same as minus 4 fourths. So finally, y is equal to negative 1/4 x. So that would be the slope of this line. It tells us if I go down 1, I should be going over 4. Yeah, that checks out. So I think the slope is correct on this one. And from here to here is the negative 1/4 x. A fourth minus 4 fourths is negative 3/4. So the y-intercept should be at negative 3/4. That actually looks about accurate. That could be negative 3/4. I'll go with that. Yeah, not too bad. So this would be the elimination of the parameter in our step 2. Any questions about that? Okay, so what's kind of interesting about this problem is a really important question is why do we need parameterization of a curve C if we can always get to this? And the trouble is you actually can't always do this. Sometimes when we try to eliminate the parameter, we do get problems because eliminating the parameter implies that y is a function of x. Y is a function of x. So important things about y being a function of x is, as a function, it must pass the vertical line test for sure, or else there's no possibility it's actually a function. And that means if in a different problem, the curve C looks like this, just some circle, and randomly in the first quadrant, just out of convenience, then we can never actually eliminate that parameter and get a single function because that curve here would fail the vertical line test. So this is the whole reason why we do need a new concept. If we want to do calculus on this as a circle, we have to go to parametric equations because there is no single function for that circle. It actually comes to functions, which would be doubling the work if we try to do calculus on that thing. Any questions about that so far? Okay. I guess I have a question for folks. Should we try this again with a slightly different problem, just for practice? Okay, let's give this another try. Maybe slightly different instructions for this one. This problem now says to let x equals e to the t minus 1, y is going to be equal to e to the 2t, and that's all we have. So this is a different kind of curve where t is any real number. So for this particular curve, what we lost is an initial point and a terminal point, but we still have a structure to the curve that tells us what the directionality would be. But this time, we're going to sketch this curve in a slightly different way. Instead of doing a table of values, which is, to be honest, just kind of mundane type of busy work, we're going to eliminate the parameter first, if we can. So we'll see if we can do that. Then if the curve is something that we know we can sketch, we would sketch it using the Cartesian form. So let's do that. This is going to say sketch the curve C generated by these parametric equations by first eliminating the parameter t. So that's our new process. Again, it is important to know that we can't always eliminate the parameter t and get one single function. So keep in mind if you want to get a sketch of this curve, sometimes you have to get multiple functions and sketch all of those, or a table of values like this is still a decent route, or the best option is just make a computer do it. So what we'll be doing in the next class, 10.2, is we'll be visualizing sketches of all the curves so we can look at the geometry of the curve itself to help us get through the problem. We're focusing on curve sketching because understanding how the curve is generated helps tremendously in getting through the calculus portions, at least with tying down the intuition of what is what and why we're making the weird kind of computations we will be making. So first things first, we want to eliminate the parameter. And eliminating the parameter, remember our goal is to write y as some function of the variable x. So let's start by taking x and solving it for t. So solve for t in x equals e to the power of t minus 1. So if we want to solve for t in that thing, the trouble now is that t is trapped inside the exponential function. So we just need to isolate e to the power of t. So let's add 1 to both sides. X plus 1 is now e to the power of t. Then go to the next step to free up t from the exponent position. What new trick do we need in this case? Yeah, the natural log is the inverse to base e exponential. So if we take the natural logarithm of x plus 1, it would become the natural logarithm of e to the power of t. And if you wrote just t itself, that would have been a decent shorthand to take because the natural log and base e undo each other by being inverse functions. So now it's natural log of x plus 1 equals t. And that's what we wanted. We solved for t. Next, we substitute this back into the value of the second equation for y. Any questions so far to that step with the algebra? Okay, so after taking natural log, then substitute. We have y is equal to e to the 2t, which is now equal to e to the power of 2 times the natural log of x plus 1 through the substitution of the value of the parameter t. So what's really cool about these functions, the natural log and base e is an exponential, is that they cancel out. Whether you write it the natural log, then the exponential, or if it went the exponential, then the natural log, they would cancel out. But this does not have a cancellation. What's the stopping thing? It's a weird way to say it. What's stopping us from canceling base e and the natural log? The 2, right? The presence of a 2 right here destroys everything. Similarly, if there was a 3 there, there would have been no cancellation at all. So we have to be careful with these inverse functions. One thing we can say is, by properties of logarithms, 2 as a coefficient can be promoted to an exponent in that way. So if we do that, then we have y equals e to the power of the natural logarithm of x plus 1 now squared. That's just the step we needed to in order to get a cancellation going this way. So whether it's base e or the natural log, if there's no coefficients in the way, we have nice cancellations just because of those functions being inverses to each other. And now y is equal to x plus 1 squared, and we have to sketch that curve. Any questions to that step so far, folks? Okay, so if we want to sketch this, we could have generated a table of points and started plotting everything. That's kind of dangerous to do if you don't know where the initial point is or the terminal point is, because there is no initial terminal point. We wouldn't know necessarily where to even start sketching on this table here, particularly column 1. But if we convert everything to a Cartesian coordinate system, if that is possible by limiting the parameter, then this is not too bad to plot. This is just a parabola with a vertex at -1, 0. Sort of. We have to be really careful here. So let's actually sketch the curve finally on this one. So first, this is incorrect as a sketch of this curve. It's going to start at -1, because if I plug in a -1 here, the y value would be -1 plus 1, which is 0, squared, still 0. So that's where the vertex is. Then for this parabola, if I put in, say, a 0, it'd be 1 squared. So we'd be at height 1. And you don't have to do a whole ton of points on this. I've assumed people already sketch these kinds of things, so you can do it very rapidly. However, that would be the entire parabola altogether. Anyone see what makes that incorrect as a sketch? To me, it's really, really horribly subtle. Somehow, some way, there's information in the original statement of the problem that tells us, well, we just plotted. It is the correct sketch for y equals x plus 1 squared, but it's the incorrect sketch if x is a function of t in this way, and if y is a function of t in this way. So there's something about those particular functions that are making this not correct. And the issue with that is the reason is that e to the power of t, no matter what, is bigger than 0. It never actually obtains 0 itself. So if we do something along the lines of looking at e to the t minus 1, no matter what, that is bigger than a negative 1. But e to the t minus 1 itself is x. So the original x had no possibility of ever being smaller than negative 1. In fact, it cannot even obtain negative 1 itself. X is always bigger than that. At the same time, we have e to the 2t is also always a positive quantity, but that is y itself. So y has to be bigger than 0, and x has to be bigger than negative 1. So this is the punchline, and it all comes from this right here. The sketch of e to the t looks about like that, where it intersects exactly at 1. It has a horizontal asymptote y equals 0, and it never meets the horizontal asymptote at all. So as soon as we wrote equations that look like this, it immediately implied, even though it was incredibly subtle, x is bigger than negative 1, and y is bigger than 0. So we have to be very, very careful with those kinds of considerations. So in that case, this sketch was incorrect because of those two conditions on the domain for x and y. So we just go over, try to sketch that original curve we did put in, and delete everything we need to delete. So this would be the correct sketch. The correct sketch still has the same vertex right at the coordinates negative 1, 0, but remember x can't actually be negative 1. It's strictly greater than it. So we would start our sketch with an open circle to communicate this one point is not a part of the curve. Then from here out, the next point is on 1, and it would look about like that. Any questions with that so far? Okay, so that would be the sketch of our curve. And keep in mind we have to do a couple things. Our sketch of the curve should include an initial point and a terminal point whenever there is one. There is no initial point here. We just approach one. We also have to have the directionality to the curve. And I would say that qualifies. That indicates it's not exactly starting there, but we're going to go somewhere, well, possibly in that direction. I'm not sure, actually. Anyone see what the directionality should be for this curve? Would you feel like it's going this way or the opposite direction? How many for maybe that way? I guess another follow-up question would be, how do we even determine the directionality of the curve? The answer is not altogether wonderful. One way to determine the directionality to the curve is to do this once again. So let's pick values of the parameter. I only need 2 values now, and I can tell you which direction the curve is being swept out. But that would be a way to do it. Kind of unfortunate because we are trying to avoid doing that. But if we want to say the direction everything is being swept out, and if we want to know for certain, then this would be a decent thing to do. So let's pick values of the parameter. Remember, t could have been any real number whatsoever because the domain of e to the t is all real numbers, and because we never put in a restriction. So I'd probably pick 0, just because it's nice. So if we input 0 into the parameter, go to the original equations for x, e to the power of 0 is a 1, so this becomes a 1 minus 1 for a 0. Then putting in for y, e to the power of 2 times 0 is still e to the power of 0, and this becomes a 1 for y. So when t is 0, we end up at the point 0, 1, which is exactly right here. So now we're going to do t is equal to 1 very next, just because it's easy. If I do t is equal to 1, keep in mind that e is about 2.7. So that's just a really rough estimation. So plugging in 1 right here would be about 2.7 minus 1, so it's about 1.7. Does that make sense for that x-coordinate so far? Okay, so plugging in 1 for y would be e to the power of 2. Oh dear. So if e is about 2.7, e to the power of 2 is about, this is a really, really rough approximation. It's about 9. It's less than 9, but I didn't want to square 2.7. So I estimated 2.7 to be 3. And I'm going to say e squared is very, very roughly 9. It doesn't have to be perfect, because my sole job here is just to determine which way the curve is going as we input values. Other questions with that so far? Okay, so now if I have t is 1, well, first this was the point when t was 0. When t is 1, we go to 1.7, which is about here, and y should be about roughly, not exactly, 9. So this is now when t is 1. And every single point on the curve is generated as t varies continuously from 0 to 1. At this stage, the curve is going this way. And we can know for certainty that it really is going in that direction. When t starts to become negative, at -1 it's somewhere out here, and as we approach to negative infinity, it'll get closer and closer to that point, but it will never hit it. It's using this asymptotic behavior here for e to the x, or e to the t, to approach the point right at that vertex. So that would be the sketch of that curve. That's a lot of work, and this stuff probably looks like it's not the funnest thing in the world, but keep in mind that these last couple problems were chosen to show you what some of the weirdest issues that could ever come up are. And to me, this is about as weird as it gets. You have to be very, very considerate about domain conditions on x and y, and range conditions at the same time. Any questions at all with that problem? Okay, so that's taking parametric curves, visualizing them, determining their directionality, things like that. The next things we'd like to do is describe how to do calculus on curves that look like this one right here. So that'd be the very next section, 10.2. I'll leave it completely optional to folks. We could do maybe one more just like this with the same instructions, or go to the next section. So what sounds funner at the moment? One more, or the very next section where we'll describe calculus on the curve? How many for one more? About half the class. A little bit more, some abstains. Maybe just one quick one, and we'll go to the next section. Does that sound all right to folks? Okay, we'll only just start it, but I think we'll have plenty of time when we come back on Thursday to complete that section 10.2. And that will be the scope of the entire homework assignment. So the homework assignment is pretty light on 10.1 because this is essentially all we're doing, just getting familiar with parametric curves. But 10.2, finally we'll start doing things like derivatives and integrals. We'll look at questions involving tangent lines, concavity, and all that great stuff. And this has the title, Calculus. That's a U with parametric equations. So first thing we should do before we get too far ahead of ourselves is we have to describe how in the world to take a derivative in this context, where we have two equations generating a curve that looks like this. So let's first go back to a sketch for a generic parametric curve. Let's say that suppose the curve C is parameterized by x and y. But remember, when we write x and y in the context of chapter 10, we're really thinking two probably different functions, such as e to the t minus 1 versus e to the 2t. So we're parameterizing by x and y, where in this specific situation, we need that y is a function of x. And at the same time, remember there should be a parameter somewhere. We're going to say x is a function of the parameter t. So y is a function of x. Note that it's telling us we should be able to go to this format in order to compute the derivatives. If we can't do that, we have to restrict our domain until we can eliminate the parameter and look at a single function. So if I want to take a derivative, if I can't eliminate the parameter because maybe the sketch is a circle, then I would have to break up this curve into two portions. If I need a derivative, say, right at this point here, I would just take the curve that goes from here to here, so the top curve. So that's one little issue that we have to correct with to get through this theorem. So y is a function of x, and x is a function of t. So that's going to be the situation that we're pretty much going to have standing for the entirety of section 10.2. We'll always assume that this can be done. So this means that y is going to be equal to, let's call this, say, how about uppercase f of x, because we're told on the onset y is a function of x, and that's what that information would produce. And we're also told x is a function of t, that's a d, and x is a function of t means x is equal to, let's let it be, say, g of t. I went with uppercase f there only because that function is going to turn into a composition, i.e. y is really f at g at t. So if we can write our function y in that way, where we originally started with a parameterization in x and y, then we can do a derivative pretty fast. We just have to specify how it should go. So let's do that next. First, let's say what we're even trying to calculate. So if I want to calculate a derivative, say at this point precisely when t is equal to 0, the derivative is going to look like this geometrically. So I need to get the slope of a tangent line, which would go about like that. So whatever this slope is, m, that's going to be dy dx. Or you could call it y prime if you like. If you call it y prime, you need to be thinking of y is equal to capital F of g at x. So we'll calculate m is equal to dy dx. This bar is sometimes called an evaluation bar. I want the derivative right at this point here. So this would be evaluated when t is equal to some value, 1. Only because this point occurred when t is 1. So that's what our derivative would look like. And that form of the derivative is just a throwback from, say, first week of Calculus 1, but also tells us what we're going for. We want to calculate dy dx. So we need a formula for dy dx. If we can find that formula, then we're all set. We can reproduce everything we've done in Calculus 1 as far as derivatives go. Any questions then about where we're going with that goal? Okay, so the derivative was the slope of the tangent line. In Leibniz notation, it was dy dx. And when you have a mixture of variables x and y that depend on a third parameter t, Leibniz notation is a really great idea because it's going to tell us exactly what is the independent variable, what is the dependent variable, and so on. So first we can say, well, if we want to calculate dy dx, the first issue is this is our y, and we can calculate a dy dt because y ultimately depends on the parameter t itself. It does depend on x because x depends on t, but ultimately it's the t that makes all the difference. I can calculate a dy dt by that, even though I want dy dx, and the x there makes all the difference. But that's just where we're forced to start if the independent variable is t. So dy dt, by the chain rule, would be equal to d, we can say df, because first if you want to calculate the derivative of y with respect to the variable t, we would have to take the derivative of the outer function first. So we can say that this is df dx, or say just dy dx, because uppercase f is y. So we could call this a dy dx. And what's cool about the chain rule Leibniz notation is it should always kind of imply a cancellation which is invalid. In other words, if I think of this as fractions, and if I cancel them to get back to dy dt, I would want a dx right here for that cancellation. Note that those are not differentials, so those cancellations are actually invalid. but it gives you the right intuition for writing out the chain rule in Leibniz notation. Dx would go here, so what should be down here? Exactly, yes, x varies with t, so we have to take the derivative of x with respect to t. And that's what should happen for y. The dt here should end very way out here. So this t has to correspond with that t. So we did it. We took the derivative of y, where y varies with x and x varies with t. It has to look like that through Leibniz notation. But remember what our goal was. Our goal is dy dx. And there it is. This is just an equation separated by multiplication. So we can say that dy dx is in fact equal to, we can take dy dt divided by dx dt, but we need to be a little bit careful. If the derivative of x with respect to t is 0, then that whole thing would be invalidated. So there's an extra condition in this entire process. So first you have a parameterization in x and y. We have to be able to get to this format, and dx dt cannot be 0 because we would have divided by 0. Dx dt being 0 means you had a vertical tangent line. That would happen, say, right here on the circle. So when that happens, we can't actually calculate the derivative because the slope of this tangent line is undefined. Whereas the slope of this tangent line, well, looks like it's maybe 2 or something like that. It's not vertical, and that's the important part. So this is undefined because it's vertical, and dx dt would be 0 in that situation. So whenever we have that formula failing, it just implies a vertical tangent line. So it's not a total failure in that sense. We would still have information about what is happening at this point on the curve. So we can say that this holds provided dx dt is not 0. Then that's the process for computing the first derivative in this context. I guess we could call this one big theorem. Any questions with that process so far? Okay, there's a couple things we could do at this stage, just depending on what we feel like doing. We could use this immediately, start calculating first derivatives, finding tangent lines, or we could see what the formula is for the second, third, fourth, fifth derivative, and so on. So what sounds more exciting to folks? The second derivative or just practicing this formula immediately? How about just go to a problem using this? Does that sound all right, folks? Okay, let's do a problem using the first derivative. Then we'll discuss how to take higher and higher order derivatives very next. So this next equation or problem says to do the following. It says find an equation of the tangent line to the curve. The curve is x equals sine t, y equals sine 2t. So find an equation of the tangent line to the curve C, given by x equals sine t and y equals sine 2t, where here we have an initial and terminal point because the domain of the variable t will start at 0 and end at 2 pi. So that's our curve altogether. Any questions about it? Questions you might have are, what is that a curve for exactly? And those are questions that we can answer by using the methods of 10.1. The problems that we run into, however, is it just takes so long to generate the curve using those methods. So if this was a problem that you were getting from 10.2 on the final exam, I would just provide that sketch immediately, and then you'd be all set. So I guess we could go to a sketch on the computer. Let's see how that goes. I think we have a way to get a quick sketch of x equals sine t, y equals sine 2t. And that sketch is really helpful because once we get the actual equation for the tangent line, by analyzing its slope and looking at the curve, we'll be able to tell if we're on the right track or not. We just have to find a good system for sketching because ISU continues to run out of money, we don't have a license for Mathematica any longer. So let's go to wolframalpha.com. I think that's the right address. That's just a decent all-purpose calculator for plotting as well. And I want to do a parametric plot of, here we'll just use curly braces. There's loads of ways to input this, so it doesn't have to be exact. I'll do sine t. So that'll be imply x is sine t, y is sine 2t. So writing out this way, it tells Wolfram Alpha that we have this situation, but it doesn't tell us the domain of the variable t. So maybe let's plot it first and decide if it even would have mattered. That's our sketch. And I think it's probably the case that if we told Wolfram Alpha to only plot from 0 to 2 pi, it would have been the same exact sketch. But let me see if we can determine how to do that. I want to do this parametric plot where 0 is less than or equal to t, which is less than or equal to 2 pi. And this is what it would generate. Just to validate how to put in the correct domain. So with the domain, this would be our curve. And we want to get the tangent line to this curve at a certain point. So let's say what that point is. So here we say we want the equation for the tangent line to that curve, and I think I've lost my notes, where t varies from 0 to 2 pi, and it's going to be at the point where t is equal to pi divided by 4. So just something nice to calculate. So that's the setup of the whole problem altogether. And this is about how it would be formatted on the exam. Of course, that would have been down there on the page so that you have a curve to look at. First thing to do is we need the slope, but that's what this is right here. So we can say that the slope is m, which is equal to dy dx evaluated at the point where t is equal to pi over 4. So that's what the evaluation would look like. Probably what I would do is go to an opposite column and just calculate dy dx. Then come back to the slope equation we're building on the left. So we can say, in this problem, dy dx is equal to dy dt divided by dx dt. Really just looks like some kind of strange incorrect quotient rule, but that's just a consequence of taking a derivative in Leibniz form and solving for just one portion of that derivative out of the 3. So it says, very rapidly, if you want the derivative, take this derivative with respect to t. We will get negative cosine of 2t, and the chain rule will give us the extra factor of 2. So that'd be the derivative of the numerator. We divide by dx dt, which is just a derivative of x with respect to t. And that would be, oh, sorry, that's a positive 2. Derivative of sine is positive cosine of t. Does that look all right to folks to that step? I deleted the negative sign. Derivative of sine is positive cosine. Must have been thinking of integration. I'll stick with that story. Any questions with the derivative so far? Okay, so there's no simplification here since 2t is trapped inside the cosine function, as is the t. But we can now say that the slope m is going to be the dy dx evaluated at pi over 4. So now it's going to be 2 cosine of double pi over 4, which would be a pi over 2, divided by cosine of pi over 4 itself. And that's our slope. Pi over 2 just because of the extra factor of 2 in the derivative on the right-hand side. Any questions about that so far? Okay, then the question that comes up is, what is cosine at pi over 2? Would it be 1 or 0? People visualizing the circles. 0, everyone agree? Yeah, at pi over 2, cosine goes to 0. And I think for this final exam, just an extra side comment, because we're doing lots of stuff with trigonometry, all of a sudden in section, sorry, I was in a weird place on the Moodle website, in section 10.3, in 10.4, we're going to be dealing with polar coordinates and curves parameterized using polar coordinates. So trigonometry is going to start to come in a big way in this exam. So I think a really good set of formulas to put either on the note card or a sheet of paper if we decide to go that route would probably be something like the trig table or any kind of trigonometry that might support you getting through stuff like this, because it's just going to come up quite a bit throughout these last problems. But first, this is 2 by 0. The denominator at pi over 4 is root 2 over 2. But at this stage, it doesn't matter. This just had to be non-zero. And the whole thing comes out to a 0. So the slope m is 0. And if we go back to the curve, we have a figure 8, or an infinity sign. There's 4 locations where we actually had a slope 0. They would be here, where there's a horizontal tangent, here, here, or here. So what's interesting about the information that was given is that they never actually told us where the base point is that we're computing a tangent line on. So we have to calculate that very next. But any questions first with getting the slope on the first part? Okay, so once we have the slope, or I guess the order is not critical, but at some stage, the next thing to do is to find the actual point on the curve at which we're computing a tangent. So we start with the parameter, and we can say we want the tangent line equation at x comma y. But recall x and y are functions. So you could say that this is going to be x at pi over 4 comma y at pi over 4, where these are just using function notations in the evaluations. Or you could have said sine pi over 4 and sine of pi over 2. So we have the point x at pi over 4 is going to be sine pi over 4. And y at pi over 4 would be y at pi over 2 due to the doubling on t. Or excuse me, sine at pi over 2. Does that look all right to folks so far? So really all I've done at this step is I've taken the pi over 4 and I plugged it in for t on x and y, and this is the point we would get. Then we have to evaluate, and sine at pi over 4 is just like cosine. It comes out to a root 2 over 2. Sine at pi over 2, that's the one that goes to 0 at pi over 2. So that's going to, hang on, goes to 1, thank you. Goes to a 1 at pi over 2. So that would be the y-coordinate on the unit circle. So that if we take root 2 over 2 and 1, then root 2 over 2 is about positive 0.7. It tells us we're going to be right about here. So what I would check where the cursor is on this curve, I have a point at root 2 over 2 and 1, roughly. Does it look like the horizontal line, or excuse me, the tangent line should be horizontal at that location? Yeah, I would agree. It looks pretty horizontal to me. However, if the point told me it was somewhere out here, I'd be very alarmed. It would tell me my derivative is probably wrong, because I would be expecting a derivative at 1 if that's where the point ends up, at pi over 4 for t. So now we know that we want the equation for the tangent line right at that point, and this is actually really, really nice. It tells us we're essentially done. Y would be equal to just the height of that curve right as it goes to that tangent line. So the equation should be y equals 1. And we're done. That was kind of just lucky, right? If I didn't have that it was a horizontal tangent line, I probably would have done this as my next step. I would have used y minus y1 equals slope m times x minus x1, and just evaluate from there, where the y1 and x1 came from the root 2 over 2 comma 1. So what was nice is that m was 0, so this becomes y minus a 1 from the y1 over there that we corrected equals 0 times x minus x1, which is root 2 over 2. But all of that is 0, so y equals 1 for the tangent line equation. But one thing that's also really interesting about this problem is notice that it probably was a good idea to do all that information first. So if you found where the point was, and if you can obviously tell that it's a horizontal tangent line, in this problem you could have skipped the derivative. Just add an extra note that y equals 1. since the curve has a horizontal tangent here. So if you told me y equals 1, with just a brief explanation of why it has to be 1 by the geometry of the problem, I would say that that's a full set of work on that entire problem. You can't possibly skip the derivative. But if it was anywhere else, we would have had to gone through the whole process. But any questions with that so far, folks? Okay, next class, it's going to be kind of a strange class because we're essentially just hitting the big ticket items that we've seen in Calculus 1 and Calculus 2. We're going to do concavity, concave up, concave down on curves. We're going to find where tangents are vertical or horizontal. We're going to look at lengths of curves, and then we're going to also look at volumes and areas. You may not hit everything, but we'll do the best we can. So it'll be about 4 or 5 different problems with different concepts each. But it should feel like a review once again, so it's not too horrible. If you have questions, feel free to stick around.